This is a video about how to define sine and cosine as the uniform limits of some sequences of functions. So maybe a way around using the unit circles, say, or triangles to talk about sine and cosine. What's kind of a more functional origin for these two functions. So again, we'll define sine and cosine as limits of two sequences of functions. And so here's the result. And so what we'll do first is we'll show that there exist two functions, c and s, whose domain is all real numbers, such that the following two things are satisfied. So the first condition is that the second derivative of c is equal to just minus c for every x in R, and the second derivative of s is equal to just minus s for every real number x. And the second condition is that c is 0 ought to be 1, c prime is 0 better be 0, and down below s of 0 better be 0, and s prime of 0 better be 1. Now you probably guessed c is what cosine is going to end up being. And if you think about, what do you know from, say, calculus, right? You take for granted. If I take the derivative of cosine, it's minus sine. If I differentiate again, you get minus cosine. So this relationship here is satisfied. Similarly, for sine, you probably guessed that that's what s truly is. We'll show that in a bit, but for right now, this s here, if you think about regular old sine, what happens when you differentiate it? Well, the derivative of sine is cosine, and when you differentiate again, the second derivative would be minus sine. And so this little differential equation here is satisfied. And then at the very end, we're just trying to say that, think about when you plug 0 into cosine, it spits out 1. And when you plug 0 into sine, it spits out 0. And similarly, when you plug in 0 into the derivative of cosine, well, that's minus sine, so that would be 0. And when you plug 0 into the derivative of sine, that would be cosine, right? So cosine of 0 would be 1. So again, this is just trying to say that these are going to be the sine and cosine that you know and love from calculus. So let's try to prove that these two functions actually exist. And again, we will call them sine and cosine later on. I'm just kind of telling you, if you feel like that's what they are, you're right. So let's prove that these two functions exist. So here's the proof. It's a little bit long. So we'll define these two sequences, Cn and Sn, as follows. So again, these are sequences of functions. So here we go. C1 of x is going to be the constant 1, whereas S1 of x is going to be the linear function x, so like the line through the origin, slope 1. Now Sn of x is going to be the integral from 0 to x of Cn. And Cn plus 1 of x is going to be 1 minus the integral from 0 to x of Sn. So again, be careful here. It's always kind of funny. Sn, x is the variable, and notice that that is the input up there. So the independent variable is that kind of right endpoint here. And what you probably guessed is we're going to be using the fundamental theorem of calculus in a little bit to do this. So these are how my sequences, again, are defined, sort of inductively. C1 is this, S1 is this, and that allows me to define the rest of the C's and the S's in these two ways toward the bottom. So what we can also note here is based on how they're defined, based on, again, kind of these inductive definitions here, each of these things is continuous. So every single Cn and Sn is a continuous function for all real numbers. And so if it's continuous, that means that it's bounded on a particular interval that you were to consider. So it's bounded on any closed interval. And remember that continuous functions on a bounded interval are integrable. Okay, that'll be good for us. So what can we do? Well, by the fundamental theorem of calculus, each one of these, think about, could I differentiate that? Well, if the thing you're integrating was continuous, then yes, you can differentiate. And so by the fundamental theorem of calculus, each of these is differentiable, and I know how to take the derivative. I know that the derivative basically just undoes the integral, and it plugs in the right endpoint where you're integrating, the upper limit of integration. So Sn prime, if you think about differentiating this, it should just be Cn of x, right? With that x plugged in to your integrand. And so again, I'm just writing that out. The derivative of that, by the fundamental theorem, I can conclude that that's just Cn of x. And similarly, if I was to differentiate this stuff here, that's what I'm saying to do. And if you take the derivative, remember with respect to x, that's what this notation is just trying to emphasize. This would be 0 when you differentiate, and this would just plug an x in for that t, and you'd have it. So this is just 0 minus Sn of x, which of course is just negative Sn of x. So my sequence of functions satisfies maybe what I suspect sine and cosine ought to satisfy, right? Where I'm saying like, okay, the derivative of each one of the functions in the sequence that's going to eventually converge to s is going to be the Cn, right? And then similarly down here, the derivative of each function that's eventually going to converge to c, which I'll show you soon, is equal to minus Sn. So it has that same relationship. So what we'll do is try to get some more explicit formulas for Cn and Sn, kind of like we did in the exponential video. So we'll show by induction that Cn plus 1 has this form right here. This should look kind of familiar to you. This is the Taylor series for cosine expanded at x equals 0. If that does anything for you, maybe from Calc 2, maybe that's reaching back a little bit too far. But if you did notice that, yes, you're exactly right. That's what it is. And so let's prove this one by induction. We won't do the sine one, it's kind of the same argument. So induction's fun though, we can't skip that, right? So the base case, when n equals 1, well then c, notice here, n plus 1 here. So when n is 1, notice I'm looking really at c2, so 1 plus 1. And what should it be by definition? Well, by definition, this is the definition of the c's, so it should be 1 minus the integral of s1. And I think that's what I wrote down here. It is 1 minus the integral of s1, and I could do that integral because I know what s1 is. S1 is just t, since t is the variable here, and when I do that integral, this would just be t squared over 2, and then when I plug in my, b minus a, or sorry, I probably should say, f of b minus f of a, the fundamental theorem of calculus, you just get x squared over 2 for this integral. So 1 minus x squared over 2, which of course, if I look at what am I trying to show, yeah, that's the first two here. So we're golden, hence the check mark. Okay, base case is good. So let's suppose that ck plus 1 has that desired form, where it looks like, what am I doing? I've got 1 plus, I really just got all these even powers of x, and I just see that the sign is alternating on each one. So I got minus, I got plus, blah, blah, blah. So just minus 1 to the k, however far out you are in the sequence. So let's suppose that that works. What we're going to do is show what happens for the next index, so k plus 2. So what is ck plus 2? Well, let's write down the definition of ck plus 2 would be 1 minus this integral from 0 to x of sk plus 1. So right, this one is one less index than the c's. That's how these things are defined. If I go back up, just where did we define these sequences of function at? Again, notice the index on the cn is one more than the index on the s. So that's where we're at down here. And let's see what we could say about that. So let's talk about what is sk plus 1. Well, sk plus 1 by definition, sorry, there's a lot of scrolling in this video. What does Sn look like? It looks like this, right? So think about putting a k plus 1 here. Well, then that matches a k plus 1 too. So maybe I should do, these things match in that case. So I'm going to write that down here. And what do I know about ck plus 1? Oh, I know what ck plus 1 looks like. It's sort of this weird looking polynomial. So let's plug that in. And notice I'm just using a different variable, u here. But I'll plug that in. So I've got this form down here. I just use u's instead of x's. And so what am I going to do? Why do I use u? Well, because I'm going to integrate. So I'm going to take the integral, or find an antiderivative for each one of these. Remember how that works? This is just a polynomial. So you just increase each of these powers by 1, and then you also divide by that new power. So in particular, like look at the first one. When you increase u squared by 1, the new exponent is u cubed, and you'll divide by that 3. So a 3 is going to go down there with the 2 factorial. Same thing here. The 4 is going to increase to a 5, and the 5 is going to wind up downstairs as well. And so maybe what do you notice? Well, you notice, hey, 3 times 2 factorial, that's 3 factorial. 5 times 4 factorial, that's 5 factorial. So we're just adding on an extra piece there. Okay, so I think I missed a 2k somewhere. Yeah, I think I have a typo. There should be a 2 right there. Anyway, we'll keep going here. So what have I got? Now what we'll do is we'll kind of bring this back in. So that was just kind of like a little side computation to justify that this should be equal to 1 minus the integral from 0 to x now of this expression, which is right here. So I hope that makes sense. All this was scratch work for what does sk plus 1 look like? And we said, this is sk plus 1. Hope that makes sense. We'll do the same kind of thing. We'll just integrate this piece by piece again. So again, we'll do our power rule. That's pretty fun. So this becomes t squared over 2. This becomes t to the 4th over 4. And that 4 is going to join 3 times 2 factorial. I think you see what's going to happen. Hey, that's really 4 factorial. And so finally what we'll do, we see at the very end, this one as well. That's the same thing as 2k plus 2 all factorial. Hope that you see that. So the pattern works for every single one of them. And the last thing that we'll do is we'll take this minus sign and we'll distribute it to everybody here, which just flips all their signs. So I get I guess I didn't want to do that, did I? I get there. Flip all the signs. 1 minus x squared over 2 factorial, blah, blah, blah. It has that desired form that we wanted. So that's the check mark. That means we did it. So by induction, yes, I can say that this polynomial is a good form of what Cn plus 1 looks like. And again, I won't do the proof for Sn plus 1, but it has a similar one. And what does it use? Notice that it uses the odd powers of x. So those are all odd powers of x. And notice also we still get some alternating sign. Good stuff. So what I mean there, plus, minus, plus, blah, blah, blah. It's just minus 1 to the nth power times the nth odd number, if you will. Okay, I'm not sure if that's a good way to say it now that I think about it. Anyway, though, I think you see what's going on. So the next thing we want to do, all right, I've got these cool formulas for Cn and for Sn. I'm going to show you first that the sequence Cn converges uniformly on any closed interval from minus a to a, where a is just some positive real number. And if I can show you that it converges uniformly on any closed interval from minus a to a, that means it also converges uniformly on the whole real line, which will be good. And so, okay, let's do that. So let's let a be a positive number. And let's suppose that x has absolute value less than or equal to a. All that's trying to say is that x is in this interval that I care about, minus a to a. So let's choose indices, m and n, that are larger than 2 times whatever this a is. So 2 times however far to the right on the number line I go. Then, what are we going to do? Let's consider the difference between Cm and Cn. And what I'll do is, notice I'm just going to write down Cm, right? That's why it's yellow. And then now what I'm going to do, I'm going to subtract Cn. Well, what is Cn? Cn goes all the way up just to this much. So I'm going to subtract that. So Cia. What do I have left? The difference would just be this piece right here. So when I subtract, that is all I get left, which is that over there to the right. And so, boom. And then what else can I do? I know that every single absolute value of x is always less than a, so I will plug in all the a's, and again, if it's helpful, think about this is not really there. Now plug in an a for all the x's that you see, so if that makes sense right there. And then by the way, when I'm taking absolute values, maybe I could apply the triangle inequality in order to justify not paying attention to any alternating sign. So hope it makes sense how we got to here. The next thing that we'll do is we will pull an a to the 2n over 2n factorial out of everything here, factor it out, and think about what you have left. So you would have a 1 from this piece here. If you factor this off of itself, you'd have 1 left. If I pull this off of that, what would you have? We would have a squared left, and then you would have 2n plus 2 and 2n plus 1. Those are the terms. So maybe what I should say is these two, or the front 2 terms on 2n plus 2 factorial. So if I pull those off, those are all I have left. I hope that makes sense how I said that. And then similarly, if I pull off 2n factorial from these, I just have those front however many terms. In other words, the terms that are in front of 2n factorial. That's all I've got left, and those powers. So then we're just doing some kind of exponent rules and doing some factoring. Now what I'm going to claim is that that is less than or equal to, well, think about 2n plus 2, that is bigger than just 2n, and so is this. So this would be less than or equal to, in other words, like this fraction is smaller than this fraction. How come? Because the bottom denominator, 2n squared, is smaller than the denominator up here. So remember, when you make the denominator smaller, you get a bigger fraction. So you get a bigger number. So again, this number is bigger than this number because the denominator is smaller. And I'm going to do that every time. So notice that I've got 2 factors here. That's why it's 2n squared. And notice here, I've actually got 2m minus 2n factors there. So it matches that exponent. That's kind of handy. And so this would be, well, what if I replace this denominator by the smaller denominator, 2n raised to that power? In other words, that many copies of 2n. Okay. So the last thing that I'll do is I'm going to regroup these since the powers match in the top and the bottom. I guess I got to get rid of that. I just want to write this so that it looks a little bit more like some kind of a geometric series maybe. And I'll use one more thing. N was chosen so that it was larger than 2a. Let's try to, let's solve that for what looks like, a over 2n, say. So 1/4 is bigger than a over 2n. Right? So if you just follow that algebra there. So what I'm saying I could do is this would be less than, replace all these by 1/4. That's all I did. So less than there. one more thing. This sort of looks geometric, except I've only got even powers of a fourth, which isn't good. Like, I don't have my good geometric series formula that it should, all add up to, a over 1 minus r, if that sounds familiar. But if I, say, square some stuff, this is the same thing as 1 over 1/16 plus 1/16 squared. So it is geometric, just the r is not a fourth. The r is 1/16. Now I can apply my geometric series formula, which would be that this stuff is less than or equal to the sum of that series, which is 1 over 1 minus 1/16, which is, again, 16/15. So that's where this 16/15 is coming from, just using the geometric series. All right, so let's recap. What in the heck just happened? What was the point of all that? I guess I got to push undo a bunch of times. There. So what we just said is that the difference in absolute value, oops, I didn't want to do that, did I? The difference in absolute value of Cm and Cn is less than or equal to this quantity here, which only depends on n, doesn't depend on x at all. And now let's think about, well, what does this do as n gets gigantic? Well, it goes to 0 as n gets gigantic. Remember that this factorial is always going to get huge compared to this exponential here. So that's why it goes to 0. So why is that cool? Well, that says that the difference between two terms in my sequence, they eventually go to 0 too, as the index gets larger, right? As the index gets bigger. So what did we just do? We just showed that the sequence Cn satisfies the Cauchy criterion for uniform convergence on this interval from minus a to a. A was arbitrary, so in fact, Cn will uniformly converge on the whole real line. So that justifies that there exists some function c that should be the limit of this sequence Cn. So c has domain all real numbers, such that, again, c should be the limit of this sequence of functions Cn. So we've justified that such a c exists. What else can we say about it? Well, each Cn is continuous, and since this is uniform convergence here, that guarantees that c has to be continuous as well. Remember the interchange of limits for continuity. And moreover, since Cn of 0 is 1 for every single n, well, then the limit function has to also have that point on its graph. C of 0 is also 1. Now, let's move on to sine. So why should such a function s exist for the sequence Sn? And we won't do too much work. You could do a similar argument to what we just did above. But if we take any real number a and choose any interval from minus a to a and look at the x's in that interval, and as long as we go far enough out in our sequence of functions so that m and n are larger than 2 times whatever that a is, then let's look at the difference between Sm and Sn. Well, by definition, that should be equal to the difference of Cm minus Cn, taking the integral of that from 0 to x. Now let's see what we can say about this integral here. I know that that's less than or equal to, so the integral of this function should be less than or equal to, well, how big is the interval you're integrating over? That would be absolute value of x. And then times the largest, the absolute value of the function that you're actually integrating. Now let's see what we can say about that. Like, well, absolute value of x is less than or equal to a. And I know that this, if m and n are this large, we just showed that that was less than this goofy quantity, a to the 2n over 2n factorial times 16/15, right? That was the point of all this work up here. So I'm just going to copy paste that. So we already did all the hard work for this part. So this is less than or equal to a times this stuff. So Sm minus Sn of x is less than or equal to this quantity here, which again does not depend on x. And so in particular, same idea, well, this factorial is going to drag everything to 0 as n goes to infinity. Therefore, what can we say? Well, this difference in absolute value, Sn minus Sm, goes to 0. And so in particular, that shows that the sequence Sn also satisfies the Cauchy criterion for uniform convergence on this interval from minus a to a, and since a was arbitrary, it uniformly converges on the whole real line. So that justifies that there exists a function capital S, whose domain is all real numbers, such that, well, capital S should be the limit of the Sn's for every x and r. And also, same idea, since each Sn is a continuous function, and since this is a uniform convergence here, that means that S also has to be continuous as well. And moreover, since 0 is a point, so 0, 0 is a point on the graph of every Sn, well then 0, 0 has got to be a point on the graph of S as well. Alright, so moving down to some relationships with the derivative here. Well, Cn prime by hypothesis is minus Sn minus 1 for all x, all real numbers x for all 1. So that was back here in the hypothesis of our function, I think, how we define these things. Where was it? somewhere around here, right? Where we took some derivatives here and here. They all have the same derivative. Okay, so moving down to here, sorry, scrolling a lot. So what do we know? Well, I know that the SNs converge uniformly to S. Well, that says that the derivatives of Cn converge uniformly. And remember, when I looked at the interchange of limits for differentiable functions, we needed that extra hypothesis that the limit of the derivatives also had to converge uniformly. Well, they do, is what I'm trying to say. So then in particular, that justifies that because C is the limit of the Cn's, it tells me that that's differentiable. And moreover, the derivative of the Cn's should be equal to, oops, I'm sorry, not Cn here, just Cn, just the derivative of C should be equal to the limit of the derivatives of Cn, which should be the limit of, from up here, just minus Sn, which of course is just minus S. So that gives me the relationship that I wanted again, that C prime should just be equal to minus S. All right, so C prime is equal to minus S. Again, ignore that n that keeps wanting to pop back up there. So that relationship holds, and similarly, S prime is going to be equal to C. Similar idea as what we just did. All right, so the last couple things, let's talk about the second derivatives. Remember that those were some things we needed to talk about. I'll quit scrolling. So C double prime, what is it going to be? Well, by definition, that would be minus S prime, which would be equal to just minus C when I actually do that derivative. So I've got this function C, whose second derivative is just minus the original. And similarly, S double prime, well, if I take the first derivative of S, that's just C, so I've got to differentiate again since it's double prime, and I know the derivative of C is minus S. So what have I got? I've got that S double prime is minus S. So S satisfies that sort of second order differential equation if that does anything for you. And finally, C prime of 0 looks like minus S of 0. Well, S of 0 is 0, therefore this is minus 0, and that's silly, let's just call it 0. And the last thing, S prime of 0 should be C of 0, which we know is supposed to be 1. So we've got these two functions, C and S, that we've shown they exist so far, and we've shown that the right points are on the graph, so that they will match up. Well, we still need to look at, I guess, that they'll match up with sine and cosine that we all know and love. But again, we kind of showed that they exist, not using anything about a unit circle, not using anything about a triangle, just that they've popped up as a certain limit of a sequence of functions, or two sequences of functions.